it? Woo-hoo! Yay. So we've got lots of folks that are Zooming, but we can't tell from the screen here. So those of you who are Zooming with us, you can ask questions using the chat, and we'll ask questions at the very end of this. We're so excited that we're able to get together live in the room and also by Zoom, and with our first brown bag of the Schuyler sisters, who's going to tell us about their stupendous summertime escapade. So let's welcome them now. Yay. Let's go.
All right, hi guys, we are the Schuyler sisters. Thank you for that intro. And we're really excited to tell you about our summer research adventures. And it's not working. All right, so just to give you a little idea of where we were this summer, this is a geographic province map of Virginia. And our study area was right in this red little box in the Schuyler quadrangle of Virginia, named for Schuyler, Virginia, which is where we coined our little nickname from the musical Hamilton. If you get the reference, we are the Schuyler sisters. So we wanted to come out of this summer with a couple of things. We wanted to understand the contact between the basement complex and the cover sequence, something that's long been a question posed and not really fully understood. We wanted to resolve the stratigraphy and depositional age of the Neoproterozoic Lynchburg group. Again, many years that people have spent trying to date and specify within the Lynchburg group that is yet to be done. We wanted to determine the age and the origin of the Mafic, ultramafic bodies, which Bel will get a little bit more into, and quantify the metamorphic conditions experienced by rocks in the Eastern Blue Ridge. We were hoping to come away with a geologic map with cross sections and an explanation for the U.S. Geological Survey and the Virginia Division of Geology and Mineral Resources. So my name is Katie, and I was responsible for mapping the northeast corner of the quadrangle. And my senior thesis and kind of focus on this region was to do with the Great Unconformity, which I will dive into later in the presentation.
Okay. Hi, I'm Bel. I mapped the southwest corner of the quad, and I led the Dopestone project, better known as the Soapstone project.
Hi, I'm Haley. I have been mapping the southeast corner, and my thesis is on the Upper Lynchburg group and its contact with the Catoctin Formation, and I've also been working on a Raman spectroscopy project with the USGS and on our social media presence.
Hi everyone, I'm Terri. I'm a returning person here. So I'm in charge of the northwest corner. I completed my honors thesis last year, which some of you may remember. It was the mystery of the shores melange. Now, I want to quickly kind of go over what was like my favorite aspects of this real quick, which was this picture is one of my favorites because it's the old, the Geo van with the new, the car that I earned my my field name, Speed Racer. You can ask me about that later. And then one of my favorite things we experienced this summer was actually, we got to see a bear. That was my lifetime goal, guys. It's all good now. All right, so before we get into like the nitty gritty and the science stuff, let's talk about what is a geologic map. So when we say the word map, the first thing that probably pops in your head is something you use for navigation. So Google Maps, Waze, whatever you use when you're driving around. And it kind of looks like from a Google map like this. It has topographical features. More importantly, what we're interested in, well, not we're interested, but people are interested in, like the roads, the creeks, some of the river names. But what geologists are really interested in is what's underneath all of that. And that is the geologic map. And this is kind of the bedrock. This is a map that I created last year for my thesis. It is of the Eastern 7 Islands. And you can see it's very similar. So you have the topographical features, but what we are caring about for a geologic map is what I said before. It's what's underneath all of that. So we have colors that indicate the rocks, and we have lines that indicate the contacts, and then we have measurements as well that gives us all this information in a picture form. Now, we don't start these projects on a blank slate. We kind of build upon the shoulders of giants, people who've done this before, but what we do is important because we are improving upon this. So, as I said, this is it from scratch. We definitely have backup. What we do in the lab before we even dive into this is we do what everybody does, academic research from previous literatures. We look at old geologic maps, and you kind of think of, well, there's already a geologic map. Why are we doing this? Well, they're old. I wouldn't say they're incorrect, but we have the technology to improve upon it and get more detailed scale of this. And of course, there's already projects done around this area. So we also look at rocks that have already been collected from previous projects and analyze them before we head onto the field. And then, of course, we use modern technology to plan our field work. And you can kind of see in the corner of the map, there's a LiDAR picture that I'll get into later. And that's kind of, you probably saw it as our title slide. We built that using that kind of technology. So we use Google Earth because it's very helpful. But the problem with Google Earth is this is kind of the thing we see when we zoom in on an area we want to go find outcrops. If one of you can put an outcrop to me in this picture, that'd be amazing. But you'll probably just see trees. So what can we do to find these outcrops with modern technology? There's a program that can get rid of all of that noise and really see it. And that program is LiDAR, which is light detection and ranging. It's a remote sensing method. And the way to look at it is that every pixel size is approximately 0.86 meters. Now, this creates, LiDAR in general creates a 3D model of the Earth's surface. So it not only gives us a bird's eye view, but a program can allow us to look at it in 3 dimensions. So we can rotate this to look at it at different angles as we want. And then it removes, what's really important for us is that it removes the objects like trees and houses and gets all that out of the way so we can see specific things, such as logging roads. Logging roads are a key feature in trying to get to outcrops because it's already made the hard work easy for us, and we just follow the road to the outcrops. So a lot of these, and when I say outcrops, they're usually indicated by these little peaks of elevation along slopes and other ways as well. And that not only is what we can see in that, but we can also see other things such as old mine shafts. This was a huge thing that we found using LiDAR technology. And so, yeah, that's what LiDAR does. It's great. So that's cool and all. We use this to plan our traverses. But before we get into what a traverse is, let's just talk about briefly what we did this summer and our general day. So we have a base camp. Usually we set up camp near the James River. And this was kind of our home for a few days. This wasn't a one-day excursion. Usually our trips lasted multiple days. So this is where we come back to at the end of the day to share what we did through the day. And it's where we start as well. Now, not all of our traverses, which is what we do to collect the data, which is when we go out into the field and travel, most of them are on land. But we actually had a really great opportunity to do one on water. And this is really great because the James River is in our quadrangle. And this is fantastic because it exposes outcrop for us. It did the hard work for us. And it gives us spectacular, spectacular images of outcrop. And sometimes we also have special guests. Some of you may remember ZFB. He also joined us in our canoe trip. And yeah, it was super fun. But like I said, most of it was on land. So let's just kind of focus on that. And of course, this is all safe. That's why there's warning signs everywhere. So this is kind of what we do at an outcrop. Everybody has like a specific job that it allows us to efficiently proceed or do a efficient procedure at each outcrop, so you can condense time and can keep moving quickly. One person usually mans the GPS, which is we use satellites to get accurate, roughly like 5-meter accuracy on where our location is in space, spatial, I should say. And then we have a person that plots the data on paper, which is also really important because that gives us pretty much live updates as we're doing it. And you can kind of start seeing patterns. And on this paper, we don't just plot it, we plot the rock type by using colored pencils to indicate which rock we are seeing. We also put measurements so we can start to see patterns of how beds are being tilted. And we might be able to see, maybe, hopefully, the context. And then the other person is the person that's really in charge of beaches. The person that's in charge is usually whoever's corner we're in, and their job is extremely important because they're the ones logging all this in their field book. And it's kind of the general observations. It's great. And then the fourth person is taking pictures, which you can probably tell that was me in this one. So some of the outcrops are fantastic and really beautiful, easy to reach, and it has a bunch of features on it. This one is of Bel, looking at a basement rock. And it was massive, so we couldn't measure things such as foliation, some of you might know. But we can see a bunch of fracture points that we can measure using a running compass, and we also see cool features like veins. And then some of these are not as easily accessible. Haley is doing the amazing feat of measuring a Lynchburg group rock basically in the middle of a creek. So our job's not always that easy. The rocks aren't that kind all the time. So remember that mine shaft I mentioned earlier? Super cool. Well, we went there, and this was one of the stations in my corner, and Chuck would not allow us to go down the hole. Very sad about that. I'm sure it was totally fine if we did. And what are we looking at these outcrops? Well, this is an example of what we see as an outcrop. We have a geologic rock hammer for scale, and to the untrained eye, this is kind of cool. It's a bunch of red rock. It looks like that. But some of us can play the hand game, and I'll help you out with that, of how tilted the bedding is. And this is amazing. We should all know, well, most of us should know, that deposition occurs on a horizontal level. So how did these originally horizontal layers get nearly vertical? That's a question we have in our head. In general, this is kind of our interpretation of what Schuyler looks like. Think of this as the Earth is a cake. You cut the cake and you pull a layer out. This is what we're looking at if we're just looking head on at it. So much scale because we're not looking at the core or anything like that. This is what it is. So we have the oldest rocks on the bottom, which is the Blue Ridge Basement Complex, which is roughly 1.2 billion years old. That is extremely, extremely old. And then the basement complex is covered by a sequence of sedimentary cover sequence. That includes the Lynchburg, Catoctin Formation, and then of course the Ebbington Group. What this is for our technodot model is that this is showing what we know as Iapetus rifti. And Iapetus is the ocean that came way, way before we know as the Atlantic. And it's a really ancient ocean, and this is kind of where we were looking at to see when continents started breaking apart. And this is the evidence for it. And now I'll hand it off to Katie to show off the beautiful thing we created this summer.
Thanks, Terry. Okay, so this is the map that we've come up with so far, our first draft of it. And you can see all the different colors, those designate different rock types, basically. Generally speaking, we can see that there's this kind of trend from, someone's clicking for me. Okay, from northeast to southwest that the rock types follow. And then generally speaking, the oldest rocks are up here in this northeast or northwest corner, and they get younger as you go to the southeast. Okay, so zooming in a little bit on my area, and I'll go back real quick just to show you. We're going to zoom in right around here, around an area called Appleberry Mountain. And this is just that blown up version of the LiDAR data that Terry was talking about. So you can see Appleberry Mountain right here reaches a peak elevation of about 1,580 feet. We were all lucky enough one day to climb to the top of it in very hot Virginia summer weather. But this LiDAR imagery is super useful, as Terry was talking about, because you can kind of start to make predictions about maybe where you can find contacts between two different bodies of rocks just by looking at the textures you can see here. So if you look closely, you can kind of see a difference between smooth and a little bit chunkier areas. And that's a good indicator of maybe where you want to start to look, or you have an idea of where a contact could be. So this is that same area, just moving over to a contour map showing different contour intervals that connect points of equal elevation. And from the LiDAR, we're able to get really detailed scales and accurate that will help us determine where elevations are. So then you see, this is the LiDAR imagery again, but with some of our stations plotted on it. You can see mine are the red stations, KC, and those are all outcrops that we were able to go to this summer. And like Terry explained, the process of figuring out what the rock type was, sometimes taking a sample, maybe making a thin section. But we've also got this blue data from a former student, Sean Driggers, that we were able to combine. And in this particular area, why it was so interesting is we were really trying to pin down this contact between basement complex rock, which is shown with all these green dots and stations, and then Lynchburg rock, shown by all these brown stations. So our goal was to really hone in here and figure out exactly where those two groups met, and getting as many stations in that area as we could. Just to give you a little bit of an example of what this looked like in the field. So when we were looking for the contact and we would come across basement complex, this might be something we would see, a granitoid. And you can see this one has some intrusions of leucogranite dikes, this lighter color. And then conversely, on the other side of that contact, the Lynchburg group, things we would more typically see would be in the right, this picture right here, this layered sandstone, or in this picture here to the left, this meta conglomerate with these really big clasts. You can see the pencil for scale. So that's probably like about a little bigger than a baseball size. So this red line is the contact that we were able to draw from the stations we collected. This is where we could best say that the basement cover contact meets the Lynchburg group. And from here, we were able to pull the elevations from this contour interval map. So we could pinpoint on exactly each point of that contact between the two rock groups what the elevation was. And this is really significant because we are able to gather a little bit more structural data from this. But first, I just want to point out something very unique about this contact is you see how it's a really straight line here, but you're going down a slope into a creek, up a little bit more elevation. It's pretty rare to see that going across such topography in such a straight line. So as I said, we could use those elevations that we were able to gather from the LiDAR imagery that gave us the very specific elevations, and we're able to create something called structure contours. So each of these lines connect equal points of elevation on the contact. So you can see, for example, the 425 following down to the 425. And this basically allows us to get an idea of what the strike and the dip of this contact is. We're able to kind of get an idea based on things in the field that we can measure with our runs, but this gives us a more general, broad understanding to confirm those ideas. So if we go back to the LiDAR data, another feature, we can put it in 3D, gives you a little bit more interpretive understanding of what the land actually looks like. You can see the valleys and the streams. You can see Appleberry Mountain, still this same area that we've been talking about. And then what's really cool is we can actually put the geology on top of it, which gives you probably a much better understanding of what I've been trying to explain. So the red line is that contact we've been talking about. You see over here on the left, that green is the basement, and to the right, Lynchburg. So we can see that this right here, you can see how steep that dip is. And I want to point out the stratigraphy. So as Terry was talking about, the basement rock, that should be the oldest rock, and then going up younger. So one would expect that the basement would be on the bottom with each younger deposit laid on top of it. But what's so unique about this situation is we have a contact that's nearly vertical. And in fact, the basement, the oldest rock, is actually slightly on top of these younger rocks. So something that I'll continue diving into with my senior research is just what tectonic geologic earth events led to a situation where we have the oldest rocks so steeply dipping and a little bit on top of those younger rocks. Now we're going to step back a little bit and go to Bel and a little bit more on her research project.
Thank you. Okay, so I want to talk to you guys, move away from the mapping part and talk to you guys about the Mafic Ultramatic complex. And you can see in the purple there, this makes some like really interesting map patterns, including our funky little Metagabro seahorse that we love dearly. But more specifically, I want to talk about soapstone, which is a really big part of this unit. So for those of you who don't know, soapstone is a hydrothermally metamorphosed ultramafic rock. So hydrothermal metamorphism occurs when chemically active mineral-rich fluids interact with the pre-existing rock in the area. And an ultramafic rock is characterized by a low silica content and a higher iron and magnesium content. So the pre-existing rock in this case was likely a dunite or peridotite, which are both olivine rich. There are a whole bunch of different flavors of soapstone, we like to say. They can be like harder or softer depending on the amounts of different minerals in them, but the typical mineralogy is like a mix of talc, chlorite, serpentine, and carbonate. And I have a softer soapstone as the lighter one and a harder one, the darker one that you guys can pass around to see. You can actually scratch the lighter one with your fingernail because it has a much higher talc content, so that's pretty fun. But some unique properties of soapstone is like I said, the talc makes it very soft, but it's also acid resistant and it has a high thermal conductivity, which just means it can absorb and hold quite a lot of heat. And that picture is just of a very nice soapstone slab. It's typically a gray color. It kind of ranges from like a lighter gray to a darker gray, even blue gray sometimes. And it's pretty common to see veins such as these carbonate veins like cutting through it. And there's also some pyrite there on the one side. So Schuyler is known to some as the soapstone capital of the world, and it really kind of was a soapstone capital of the world for many decades, until a dramatic decline in like the mid to late 1900s-ish. But the impacts of the quarrying can still be seen even in the LiDAR. You can see those like cookie cutter shapes here. And those are all over the place. Those are the old quarries, and then most of them have these like big piles next to them, and those are like waste piles. So they threw all the old rock and rubble that they didn't want to sell into these big piles. And this is just a very small area within our quadrangle, and there's only 4 quarries here, but in reality there's like 80 to 90 cores in and around Schuyler, or quarries, I mean, sorry. And these are very useful in mapping because we can look for these cookie cutter shapes in the LiDAR, and wherever they are, we can just assume that that is part of the Ultramatic complex without necessarily having to go to that spot and see it for ourselves. And on the right is a picture of one of the old quarries. They typically fill up with water, and they just are really spectacular to see in person. So if you can ever go see one, I highly recommend it. And a company called Polycore, about a decade ago, they just bought some of the old properties, some of the old quarry properties, and they started selling soapstone again. And within the last year or two, they started a drilling project to try to find like the best quality soapstone to sell. And here on the map, you see CL1, CL2, and CL3. Those are 3 coring locations where they drilled core at the old Climax quarries. So a big part of our summer was logging this core. We would look at about 20 feet of core at a time in those 4-foot long boxes here. And we would count fractures, we'd count veins. We'd take notes on the mineralogy of the rock and how it changes with depth, and also look for any significant changes in rock type in the core. And we get some quantitative data too with the Schmidt hammer, which measures compressional strength of the rock, which is related to its hardness. And we'd also use a portable XRF analyzer that Terry is holding right there. And that can help us determine the general chemistry of whatever sample we decide to zap with it. And we can use all this data to make various figures. The one on the right is one that I stole from Gabe Mojica in his senior thesis that he presented on last spring. He made this lithologic column using core from the Climax quarries. So this is really useful in just seeing how the lithology of the core changes with depth. So you can see not only did we find foliated soapstone and massive soapstone, but there's also some myelinated gabbro, some diorite, and even in some other cores we found felsite. And this is the longest core that we drilled. It's over 400 feet in length, and we drilled all the way through the soapstone body into the metasedimentary Lynchburg group, which is pretty cool. Yeah, also while logging the core, we pick out samples to bring back to the lab, and we end up cutting a lot of those. And here's a picture of Katie using the rock saw, cutting away, doing great. So we cut those either into like chunk sizes to send off for whole rock geochemistry, or we cut them into little billets to send off to be made into thin sections. So here is a thin section of a massive soapstone from the Climax 1 core, and this is in plain polarized light. Like I said before, there's a whole bunch of different flavors of soapstone, but for now we're kind of just referring to them as like massive soapstone or weakly foliated soapstone, etc. But one of my goals for later on is to come up with like a better and more detailed way to name all of these different flavors of soapstone. But this particular soapstone contains serpentine, talc, and carbonate, and here it is again in cross-polarized light. This green stuff in here and there, that's serpentine. The gray is a carbonate grain, and a lot of this blue and orange is talc. But not only did we find soapstone and mafic rock, but you might have noticed in the lithologic column, we also saw some intermediate and felsic rock. So this here is a fine grained diorite with a really nice feldspar phenocryst right here in the middle. And there's also some carbonate over here, and the rest is just kind of quartz and biotite. But this is a very nice euhedral shaped feldspar that we would expect to see in an igneous rock. And intermediate and felsic igneous rocks are very exciting because they typically contain zircon. And many of you know we can use zircon. We can date zircon with uranium and lead geochronology. So basically we can figure out the ratio of lead to uranium in zircon grains and use that in a calculation to figure out the age of the rock. Which brings me back to our stratigraphic column. So the purple, the lighter purple and the dark purple is the mafic ultramafic complex. And our working hypothesis right now is that it is a differentiated sill. So what that means is that the diorite and the soapstone actually originated in the same melt. So they're the same age, they intruded at the same time. So by dating the zircon from the diorite, we can figure out an age for the soapstone and for the whole body, which, if you remember, was one of our big goals of this project, was to determine the age and origin of the mafic ultramafic complex. And this is really exciting because this complex has been really enigmatic. Like researchers have been studying this for like 100 years, and there are theories on its age and origin, but there's no like definitive answer. And we finally have the tools and material to figure it out. So hopefully by the end of my thesis project, I'll like have an age for this complex. So you'll hear more about that later. Anyway, I'm gonna turn over to Haley to talk about more of what we've done with USGS this summer.
So we've been talking a lot so far about sedimentary and igneous rocks, but in our study section, really all of these rocks have been metamorphosed. And what's everyone's favorite metamorphic mineral? Graphite, obviously. So during our fieldwork this summer, we were joined for a week by Dr. Rebecca Stokes and Dr. Aaron Jubb from the USGS, who are working on testing a portable Raman spectrometer to find peak metamorphic temperatures in graphite-bearing rocks. Raman spectroscopy measures vibrational modes of molecules that shift as the molecules are hit by a laser. In geology, this can be used with graphite-bearing rocks to collect geothermometry data and figure out peak metamorphic temperatures. Usually, this is done in thin section with using a microscope with reflected light. However, Aaron and Rebecca's goal is to test the use of a portable probe using hand samples, rock powder, and slabs, as well as to standardize the methods for constraining peak metamorphic temperature of graphite-bearing rocks. This portable technology would allow one to gather geothermometry data in the field and is a lot less expensive than a typical large lab spectrometer. The images above were both taken by Rebecca and show us in the field with Aaron in the pink carrying a portable spectrometer. And there's the instrument. And this next slide shows the portable probe in action, both in the lab and out in the field. In both images, you can see we're wearing dark glasses and the object that we're testing is covered in dark cloth. This is for two reasons. The first being for our safety. The probe is shooting a laser light at the object, and this could really damage our eyes if we aren't careful. The second is that it is light sensitive and extraneous light could impact our results. With a stationary spectrometer, you wouldn't really need to wear the glasses, but all of the lights in the lab would have to be turned off and the windows all blacked out. And you definitely don't want to look right at the laser as it's shooting, because that would be bad. There are several options for the laser size on a stationary spectrometer, but the laser used by the probe is 785 nanometers. But the accepted standard laser size used in previous work for the stationary spectrometer is 532 nanometers, which is pretty different and can use different settings and output data at different wavelengths. Because of this, for each sample we collected data using the stationary probe on both settings, the 785 and 532, and we collected using the probe at the 785 setting with hand samples and rock powder and sometimes slabs. This image is a thin section from a sample we named 21 Amherst. The graphite is outlined in hot pink, and this is a very zoomed in picture, but you can see here the graphite is still pretty small. And this is actually one of the larger grains we were working with. So they're pretty hard to find, and the laser has to be hitting the graphite grain directly to be able to get a reading. So in thin sections, this can be pretty difficult to find, even if you think a rock has a lot of graphite in it, because the grains can be so tiny and widely dispersed. Yeah, because of this, since the laser is directly on the grain, you know it's going to be very precise. However, with a portable probe, rock powder can be really easy to get a reading with, because you just stick the probe in the powder and it's pretty homogeneous and you're going to hit graphite. And with a hand sample, you can just put the probe on a fresh face and look for graphite and get a reading. but you're going to have some interference from other minerals that the laser is hitting as well. So on this slide, on the left is the stationary laser, and you can see all these peaks are super clear. And so you really were just getting graphite there. Whereas on the right, you can see that there's a lot of noise around it. You can still see the peaks, and you're definitely getting readings of graphite, but they can be a little bit harder to see and a little bit testier. The peaks are here. This one is the D1 peak. This is the G peak, and this little one is a D2 peak. It's not always there, but it depends on the peak temperature of the rock. The D1 peak and the G peak are always going to be there if you have graphite. And to get the peak metamorphic temperature from any of this data, it's first processed through a software called IGOR to find a best fit curve, which you can see our best fit curve in the blue. And after you get that curve, you export the data and plug it into a formula that we derived from a paper Koketsu et al. 2017, in which the peak metamorphic temperature is a function of the full width and half max of the D1 peak. So right here is the D1 peak. That's about halfway. So this width is what you're using. So far, with the data that we've collected, the results show peak metamorphic temperatures range from lower to upper green schist facies, as well as the lower amphibolite facies, consistent with the regional geologic history of the samples sites that we've been collecting at. So that's what we've been doing with the USGS this summer. And from all of our work that we've done with different partners and our different mapping areas and theses, this is the map that we've come up with so far. It's our first draft. It's definitely going to change as we continue to do our research. And this is sort of our progress. If you liked what you've heard in our brown bag today, like, comment, and subscribe to follow our TikTok account. Woohoo! You can find us using the @GeoSchuyler Sisters and under the Structural Geology and Tectonics Research Group on William and Mary blogs. Wait. How do I get it to go forward? Oh, there we go. Lastly, big shout out to our advisor, the man, the myth, the legend, Buck Chaley, our fearless leader. Questions?
Yes, Casey. I have a question, and it is: do rocks have veins? So yeah, kind of hard to take. Guys, feel free to jump in on this, but not veins in the traditional sense of veins, obviously. But that's just a word we use for different rock that's intruded into, let's say, older rock. So we refer to them as veins because they kind of have like a vein-like.
Okay,
But yeah, good question.
interesting.
Any other questions? Oh yeah, I'll check the chat box.
Click more.
Oh. Here you go.
Okay. What was being mined in the mine shaft from James Chapman?
Yeah, it was zinc. Yeah.
Okay, it was zinc being mined. Oh, now I'm doing it wrong too. Okay. Gabe. From Gabe, when he was working with the Soapstone, the XRF didn't really give him the most accurate chemistry, just trend. I'm sure thin sections helped, but were you able to determine a more precise chemistry using the XRF or any other method?
We haven't, I mean, we're sending the rock out for, we're sending the samples out for whole rock geochemistry, and we have tried using the XRF again. I think we used it a little differently than how Gabe used it. And I'm not quite sure how accurate that is. I think we might in the future try like crushing up that rock and trying it again, because I think with a more homogeneous sample, we get better results. But we will have like more data with the chemistry when we get the whole rock geochemistry back. Yeah. Do we have other questions?
Is there any more? I thought it was at the bottom.
All right.
Yeah, that's at the bottom.
Okay. Any questions from the room? Should they do the TikTok for us right now?
We can take a TikTok with everyone here.
You could stay in the camera though, so people can see you. Sorry.
Oh,
you gotta
sorry.
be in the camera.
I can stay in the camera. I'm gonna take a video and this is going on our TikTok then.
We have to take it.
No, just do a thumbs up or
You can do a
something.
little shimmy if you want. Yeah. All right.
Also, if you don't want to be in our TikTok, just tell me afterwards and I won't post it. I'll stay in the camera too.
Okay, well, if there are no more questions, we want to thank you all. Thank you for the first brown bag. Let's say you're gonna log off now, so thank you.
Okay.
Thanks for
Thank
coming,
you.
everyone. Bye, Mom.
Go ahead.